Hi, welcome to R2E. In this video, we will be solving problem number 3.11, that is spinning loop, from Daniel Kleppner and Kolenkow. So let's see what the problem says. So it says you have a piece of string of length L and mass m that is fastened into a circular loop and set spinning about the center of the circle with a uniform angular velocity omega. Now, in this problem, we want to find the tension in the string. So a little suggestion is given here that we should draw the force diagram for the little piece of the string which subtends an angle delta theta at the center. Okay, so let's first look how our system looks like. So this is, say, my string around the loop. Now this is the center, and this angle is delta theta, and let's just say this length element is dm, and now you have two forces here. I'm sorry. So we have these two forces. So in principle, dm is really small, so it's just to draw. It's just a problem with the drawing. So in principle, these two tensions, they come out of a single point because dm is really small. It's a really small length element. Okay, so if I draw the diagram here more clearly and a more correct one, because in principle dm is not supposed to have any finite size. So okay, let's just also make it from delta theta to d theta, just for sake of convenience, for my convenience. Nothing changes. So this is t, and then you have a straight line radius, and then you have these. Okay, right. Now this is delta, sorry, again, mistake, it's d now. So this is d theta by 2, this is d theta by 2, and now in principle, so I can resolve this t into two components. One that is along this horizontal, you could say this would be theta cap, and one that is along r cap. So along theta cap, the tension will be t cos d theta by 2 theta hat, and along the r, okay, so along the theta, and so this part will give you t cos delta theta by 2, and probably the other one will give you minus of t cos the theta by 2 theta hat, because they both are in opposite direction and they sum to 0. So there is no net force in the theta direction. Now in r hat, so if we resolve it, we will get t sine d theta by 2, and again we will have t sine d theta by 2, which is equal to 2t sine d theta by 2. Great. Now if we equate this to the centripetal force, that would be 2t sine d theta by 2, that is equal to dm omega squared r. So sine d theta by 2 equal to d theta by 2, so that will be d theta by 2. Now for dm, that is capital M and d theta upon 2 pi. It has to be 2 pi. I mean, you can also do this in length, but then you have to make sure that this ratio is dimensionless. So you can in principle do it like okay, let's just do it something like this. L and R is L upon 2 pi. Okay, so just a small thing. So you can write this thing also as dr upon L, but then you have to also always make sure that this is dimensionless. I'm sorry, this is dimensionless, so that the mass still have its dimensions here, and in the dm also the mass has its dimensions. Okay, so d theta cancels, 2 cancels, and this is m equal to tension equal to m L upon omega upon 2 pi squared. It's fairly simple, and with this our problem ends. See you in the next problem.